All right. So welcome to our free GMAT prep hour for July 1st, 2020. We're going to talk, like I said, about quadratic equations today and quadratic patterns. Basically, want to make sure you're comfortable with your special products that will show up over and over again in quadratic equations, and then make sure you're getting good at applying these things. Sometimes in data sufficiency formats, sometimes in problem solving, but make sure you sort of know what you can do and what the tricks are that are available. So if you've been studying for a while, you've probably memorized these, or if it hasn't been long since you took algebra class, you may have memorized these. But there are three patterns that everyone who takes the GMAT absolutely has to know. And I don't say this all the time. In other words, I'm not constantly bothering my students to memorize endless lists of things, although there are plenty of things we could memorize. But these are absolutely essential. If you don't memorize these, you're just not serious about the GMAT. So we want to make sure we're good on these. So what I'm going to ask you to do is pull in an A when you've had a chance to try these, and you think you have, you think you know what they are. So maybe some of you are already, hey, know these, done. Some of you want a chance to play with them and see what you get. So pull in an A whenever you're ready to talk about these. Okay, so if you're one of the people who pulled an A right away, you probably have all these memorized. That's great. If it took you a little longer, if you're working them out, it's fine to keep doing them, out as a FOIL, basically, which is how we learn our quadratic equations when we're first studying them, right? We put them out and we say, okay, what's x times x? If I were to run, for instance, this one, right? What's x times x? What's x times negative y? What's y times x? What's y times negative y? And it's fine to do that, but eventually these are three that we want to just know. One reason is, of course, they'll ask about them a lot. Another is that they'll often do it in the process of something else. And so if I just happen to know them, or like I just happen to be able to do them, it's not enough. I have to know them so well that I recognize them even when I'm not expecting them. We'll look at some applications where that becomes very important. So let's look at this first one. If I do x plus y quantity squared, all right, you call this a square of a sum, what do I get? What do I get when I do that? We'll end up squaring the x's because we'll FOIL that out. We'll end up squaring the y's, and then we'll have two of the middle. And so you can think of this as x squared plus 2xy plus y squared. And the idea would be, if I were going to write it out, that I'd say, okay, same idea as the other one I was doing. You think about your first outer, inner, last, or FOIL, if you remember learning that. X times x, x times y times x, and y times y. So I'll end up with one of x times x and one of y times y. That looks really sloppy. And I'll have two of the middle one, x times y and y times x. Okay, so that's what I want to get that. And so if I change it to x minus y quantity squared, most of this should stay the same, right? I'm still going to be multiplying x times x, and I'm still going to be multiplying negative y times negative y, which gives me positive y squared. In other words, I won't be multiplying y times y, I'll be multiplying negatives, but two negatives make a positive. So the only thing that will change, I can run this out if I want, but the only thing that will change is that middle term. And so one thing to get used to, if you just memorize it, it might be kind of confusing. Which part's a negative, which part's positive? But if you memorize it with meaning, with purpose, and say, okay, well, a squared thing is always going to be positive. So my x squared is going to be positive both times. My y squared is going to be positive both times. The only thing that varies is this middle term. Is it plus 2xy or minus 2xy? Whether this actually is positive, of course, depends on whether x and y are positive or negative, right? If x is positive, say, and y is negative, then this term will actually turn into a negative, and this term will turn into a positive. But whatever we have, a squared thing is always positive for our purposes, okay? Or zero if we had a zero. But if we had a zero, we wouldn't have to do all this work. Okay, and then finally we have the third one where we have one of each. And the idea of one of each is that it's the only way I can have to cancel the middles out. Okay, so what do I get when I multiply a sum and a difference of the same numbers. How do I get that? So the x is still squared. The y gets squared too, but notice I'm going to have a positive y and a negative y. And so what happens is the middle term gets eaten up. Yeah. The middle term gets eaten up. So this is the one time where I will also have a negative y squared because I have a positive and a negative being multiplied together. And that's how I can get a negative, right? That's how I have to get a negative then. So if you were to think about this again as sort of FOIL, first, outer, inner, last terms, if you've memorized that acronym, we're saying x times x is x squared. X times y is minus xy. So we're going to have x squared minus xy. And then we'll have up here, we could look at it this way, y times x is positive xy. Maybe this is all very elementary too. Don't worry, it'll get harder. And then y times negative y is minus y squared. Okay, so those middle two terms, matter and antimatter here, they just kind of cancel out. I've got x squared minus y squared. So these are things, if you don't have them memorized, put them on flashcards, tape them to your refrigerator, tattoo them on your roommate's forehead, whatever you have to do, or, you know, whatever is going to get it to you, right? Get these things down and make it automatic, okay? And like I said, one reason we need these to be automatic is that they won't just get presented on their own, they'll get presented in context of other kinds of problems. So I'm going to show you 3 different problems, and I'll give you a hint. All of these 3 problems involve the last of the 3 patterns. The third pattern is probably the most common pattern, although they all are important. So let's look at that. So these will all use this pattern. See if you can see how it applies. Again, pull in an A when you're ready to discuss all 3 of these. Okay, let's see what we can do with these. So for this first one in the set, it might not look like any of the patterns, but if we can cheat a little bit and know that it involves the third pattern, what can I do with this? What move do I have available? Alexandra is saying I can pull out something, right? I can recognize that, hey, x to the 4th is a squared term and 1 is a squared term. Yeah, exactly, right? So the basic idea is that I don't have to have a 2 and a 2 to say, hey, this is something squared. X to the 4th is x squared squared. And 1 is, well, 1 squared. So I can factor this down. And if I recognize that I can factor that down, I can factor it even further. And so we can then break down not the x squared plus 1, but the x squared minus 1 step further. got a couple of questions I'll just answer live real quick. One question was, what grade level of math is on the GMAT? A lot of this, it depends on when you went to school and where you went to school. It's math through algebra and geometry. There's no trig, there's no calculus. So many people learn this in junior high and high school. I know standards have changed. Some parts of the GMAT are things you might have learned in 5th grade. That doesn't necessarily mean a 5th grader or a middle schooler or a high schooler would do terribly well, because they can be applied in some really annoying ways. And I have plenty of students who are engineers or math majors who still struggle with the quant part, partly because of timing, but also because the way the questions are asked is not always very straightforward, and data sufficiency is one part of that. I also had a question if we have free prep hours about data sufficiency. We do. So if you go into YouTube, that's where these are all posted. You can search for that. I have one. I'm going to do some data sufficiency today for sure. I have one on divisibility and data sufficiency. We have some general ones, I believe, about data sufficiency. So yeah, we do cover that a fair amount. Okay, so that's the first one. Second one, again, might not look like any of the patterns. What can I do here? Certainly, if I wanted, I could just work this out. I could say what's x times 2, and what's x times minus x, and what's 2 times 2, and what's 2 times minus x. So I want you to know how to do those things, but often there'll be some shortcuts. And one thing we can do here is get these in a similar order. And again, it's one thing when I'm telling you, hey, it's going to be this. It's another thing when you're in the middle of the test trying to figure stuff out. You don't even know in advance that you're going to be dealing with quadratics. It might be less obvious, but I can just rearrange the order of these, right? All I'm doing, I haven't changed anything. I've just written it differently. And now, and so, yeah, I got one response of take out a negative, factor out a -1, which is cool, but I don't even have to do that. If I can just move things, I don't even need to go surgical and throw a negative in there. I can just say, hey, x plus 2 and 2 plus x are the same. And then I can recognize, once again, I have a sum and a difference. It's this third pattern, difference of squares, 2 squared minus x squared. So again, it saves me some trouble, right, if I can recognize these pieces. Sometimes you might wonder what the point of all this is. Like, if I have something nice and compact like x to the 4th minus 1, why would I ever want to turn it into this mess? But if I had it in a fraction, I was trying to cancel things. If it was being asked on a data sufficiency question, I'm trying to figure out which part of this I had and which part I didn't have, it can make a really big difference. Right? Okay. Then finally, we had this kind of oddball question: what's 102 times 98? To which you could say, well, let me just find out. Now, of course, on the GMAT, outside of the integrated reasoning section, you don't have a calculator available. So with a calculator, this is silly. It's child's play. Why would they even ask? Without a calculator, I could do it. I could sit there and get out my paper and put 102 times 98, and okay, 9 times 2 is 16, and carry the one. I don't want to do that. At the very least, I could estimate, right? I could say, you know, you might not even need to do a shortcut for this, because maybe you can just say, hey, 100 times 98 is 9,800, and then 2 more, I'll just figure that out. But I want to show this more just to show how it connects to special products than that you have to do it this way. And so I see some of you typing it. Yeah, if I can recognize that, hey, one of these is 2 more than 100, and one of them is 2 less than 100, I can recognize a special product here and think of it as, oh, it's 100 squared minus 2 squared. Why is that nicer? Because I know what 100 squared is. It's a 1 with 4 zeros, right? 100 with 2 more zeros on the end. I know what 2 squared is, I hope. And so then I can get the answer a little more simply than if I have to say what's 9,800 plus 2 times 98, and it's 196. I can do that too. But you know, just looking for patterns. Another way you might do that, interesting, is when you're trying to factor a number to begin with. One problem I remember doing, I was trying to factor the number 399. Let's put it in the corner here. And so if I can recognize that 399 is a difference of squares, then I could say, oh, 399 is 400 minus 1. And so that's going to be 20 squared minus 1 squared. And so it's kind of the reverse of what we just did, which is 21 times, 20 plus 1 times 20 minus 1, which is 21 times 19. And again, you might not find this any easier than doing a little factor tree, right? Factor tree would look like, hey, 399, I can't divide it by 2, but I'll divide it by 3. But I might get stuck. I might say 133. Oh gosh, I don't know what goes into 133, and I might spend a lot of time thinking about it. I might recognize it's really close to 140. So if 7 goes in to 140 20 times, it'll go into 133 one time less. And so I might then recognize, ooh, I can make 3, 7, and 19, right? But this might be a faster way to do that. And so they're just depending on the situation. Sometimes it's very large terms, right? Maybe they're talking to me about what something like, I don't know, 3 to the 12th minus 2 to the 12th is. And I'm like, oh, those are really big numbers. But maybe if I can get it down to something smaller, 3 to the 6 plus 2 to the 6 times 3 to the 6 minus 2 to the 6, maybe those numbers start to be manageable enough where I could actually start to factor in. So this is where knowing these patterns can be very valuable. And you can see the value of having memorized them, because then you might think of them even when your attention isn't being called to them. If you found these hard enough when I boxed this and said, hey, these are all going to involve the difference of squares, you can imagine they're that much harder if you're not expecting that, if you're not looking for it actively. Okay, questions on this part of things before we move on? Okay, so let's try applying this to some situations. And what I want to do, it's a slightly odd exercise I haven't done before, but I'm trying something new. I'm thinking about if I have a pair of equations. You know, think about if I'm in, say, a data sufficiency problem, and I'm trying to figure out, can I get C or E, right? Do I combine these or not? I might want to think about what it is that I know and what that allows me to find. So just a quick example. What if I know that X plus Y is 7 and XY is 12? My question is, which of the following can I find? Can I find X? Can I find Y? Can I find the difference? Can I find all these various special products or combinations? So see what you can do. I'm going to give you about a minute on this to try it out, and then we're going to discuss. So see what you can do for about a minute. Okay, so I had an interesting question in the chat, which is, do we know if X and Y are integers? Now, it's a fair question to ask in a sort of informal setting like this, because maybe I meant to say they were integers and I just didn't put it, right? On the GMAT, they're going to be very careful about that. In fact, what you may have found when you do GMAT problems is it gets rather annoying, because on a lot of problems, they'll kind of lull you into complacency. They'll keep saying, for integers X and Y, or if X and Y are integers, or XY are integers, you know, greater than 0 or something like that, and they'll specify that things are integers. They'll specify that they're not 0, that they're not negative, that they're not fractions, etc. And then when you start assuming that they are, they won't specify. Right? I always think of it like a salesperson who keeps selling you stuff and say, oh, don't worry, money back guarantee, and they finally sell you something really expensive, and they didn't say anything that time. So the GMAT likes to mess with us a bit like that. So it would be interesting to see, are there answers that would change if we knew that X and Y were integers? That's an interesting thing to think about. So which of these, if any, did you feel that we do know based on this information? If I know the sum of X and Y and I know the product of X and Y, are there some of these that I can find? What were you able to find? Okay. So if we recognize our pattern, we want to definitely know that we can find X squared plus 2XY plus Y squared, because those match up very closely. Whoa, that was a solid. I wanted to let me try that again. Those match up very closely. If I just square this pink one, I get this, right? This is equal to x plus y squared. So we just automatically know what that is. I don't even need the other equation for that. Okay. Now, Jay, you're saying I can also get x squared plus y squared without the 2xy. How do I do that? So how would I get this one at the bottom? This isn't one of our special patterns, right? This is a special pattern. This one isn't. How would I get this one? Yeah, if I know that this, take away the 2xy, right? So if I take away the 2xy, I get that other one. Well, I know that 2xy is 24. So I know this is 25. In other words, another way to think about it is that if I know what that this squared, x squared plus 2xy plus y squared is 49. And if I know that 2xy, if I know what this is, right, that this, I mark it, that this piece here, I know that value, and I know how to double it. If it's 12, double it is 24, then I can find that other value. So I can definitely find this, exactly. Okay, so then I saw someone talking about x squared minus y squared. Can we get that? If I know x squared plus y squared, can I get x squared minus y squared? Do I know which is which, so to speak? Right? Is it like 24 and 1 or 13 and 12 or things like that? Do I know? And does it depend on whether they're integers? Clearly, for instance, there's only so many ways to multiply to get 12, right? Either if I think about integers, 1 and 12, 2 and 6, 3 and 4, 4 and 3, you know, can start flipping them. 4 and 3, 6 and 2, same numbers, right? With non-integers, there's lots of possibilities, but notice that that won't really help us with our addition. In other words, if x and y are two numbers that multiply to 12, whether they're integers or not, they're not necessarily going to add up to 7. So what numbers do you think x and y are? What does it seem like x and y must be? Maybe you did the work out. 4 and 3, right? 4 and 3 add to 7, 4 and 3 multiply to 12. That's not because we know they're integers, that's just because that's what works. If I had non-integers like 24 and 1/2, well, those multiply to 12, but they sure don't add to 7. And if I had non-integers for x plus y, let's say they're each 3.5, those definitely add to 7, but 3.5 times 3.5 is not going to be 12, right? It's going to be, well, you know, 49 fourths, right? It's close to 12, but not quite. So we know they're 3 and 4. So can we say, great, x is 3, y is 4? Not necessarily. Why not? Yeah, we don't know which is which, right? So sometimes we have that situation. Obviously, the question wouldn't ask us, let's say it's data sufficient, the question wouldn't ask us what's x plus y, because that's given, right? But we know when we have an equation like this, we might be able to find x plus y. So if I had x squared plus 2xy plus y squared is 49, I could find x plus y is 7, but it doesn't tell me which of x plus y is which, right? So I know that they're 4 and 3, and I even know that they're complementary. In other words, if x is 4, y is 3, and if y is 3, x is 4. Like, I know that, but I don't know which is which. So I can't find x and I can't find y. And it's not because I don't know if they're integers. They are integers. These are the only values that work for this pair of equations. But it's that I don't know which integers they are. Okay. So for the same reason I don't know x minus y, I know it's either 1 or -1, depending on which one comes first. Notice that I can know a sum without knowing a difference, partly just because of directionality, even if I know exactly the numbers they are. Even if I know, hey, they must be 3 and 4, and therefore I know the product. But unlike sums and products, which are commutative, differences and quotients, subtraction and division, depend on direction. So even if I know the exact numbers I'm dealing with, it changes depending on what I'm asking, right? Which one is getting subtracted from or divided out of which? Okay. So I don't know that difference, and for that same reason I don't know that difference, I don't know this one. And I don't know this one either because I don't know enough about the relative value of them. You can imagine if x is 4 and y is 3, that's going to be a different answer. So it's either 16 minus 9 or it's 9 minus 16, and those are different, right? So I don't know that either. Okay, how we feel about that? That makes sense? So just two that I know, right? I just know the square of the sum and the sum of the squares, but those are the only ones I know. Okay, and this is important in a data sufficiency context, or in even one of those like statement 1, 2, 3 contexts, right? Yeah, so in the original question, it's telling us x plus y is 7. So I'm imagining that that was given in the question, either in the question stem, or maybe it was a data sufficiency where that was one of the statements. Hey, if you're sleepy in the UK, definitely check us out on YouTube later. This will be up there at that time. All right, cool. Let's try another variation. What if I know the difference and the product? So again, take about a minute and see if you get different ideas about this. All right, so let's see if we know what this said. It's very similar to the last one, except this time, and obviously I'm assuming this is a different x and y, which they'd have to be, because 4 minus 3 isn't 2. So if we know this, if I know x minus y is 2, and xy is 15, what else can I find out? So how would I proceed? What's something that you can start with? What's something you can find pretty readily? All right, so we can directly find out this square, right? And that's just knowing our pattern. Again, if I know that x minus y is 2, then I know x minus y, that 4 is equal to x minus y squared, which is going to be x squared minus 2xy plus y squared, right? So we know that one for sure. And that just like the pink version of the last one, we can sort of say, hey, this, I just square this and I get that. Okay. Now, I'm also seeing, hey, 2xy is 30. So if I know 2xy is 30, similarly to before again, I could add 2xy to both of these and figure that out, right? So if I were to add, if I knew 2xy is 30, just double that, then I could add 30 here, and I can add 2xy here. It's the same thing, right? And I get 34 equals x squared plus y squared. Okay. So I can get that. Oh, did I erase that one? I meant to have that as one of the things that we can get. Sorry. So yes, we can get x squared plus y squared. I didn't give that as an option, but we can get that. Now I have some people saying we can get some of the other ones. So how would you do that? How would I get, say, x squared minus y squared? or x squared plus 2xy plus y squared? How would I get those? Yeah, it seems like we might be in a similar position, right? When we know we square one of these, we're going to get a combination of x squared plus y squared and 2xy. So it seems like it's hard to get a difference, right? Interestingly, also, we might think about if we know something about, say, x plus y or x minus y, right? So if we know x squared plus y squared, it seems like we should be able to add 2xy or take it away. And in fact, oh yeah, we were premature, weren't we? we do the same thing with the other one, right? Sorry, I should take that back. This is my first time teaching this set. This is a new one. Of course, I should be able to do this one as well, right? So on the left-hand side, if I know x squared plus y squared, then I have to know that this is just 1, right? Apologies. And same thing here. If I know x squared plus y squared is 34, and I knew when I didn't have that added in, this is just 4. If I go the other way, if I add it in, I'm just adding 30, and that's 64. Yeah, apologies about that. We have that same one. So interestingly, we have a lot of the same stuff, right? Okay. So both times we were able to get these 3. Left that out before. But it seems like it's hard to get x squared minus y squared because that's a difference of squares. Now I do know the difference, but that's a bit different from knowing the difference of squares. It does tell me something interesting. It does tell me that x is bigger than y. So one thing I might want to think about is, what are my possible values of x and y this time? If I just say, hey, what's a pair of integers that have a difference of 2 and multiply to 15, it seems like 5 and 3. So do I know that x is 5 and y is 3 then? We have to think about some possible negatives here, right? We know that x minus y is a positive integer, you're right. But if we think about it in terms of a negative, can you think about if I have negative numbers that made 15, right? Yeah, what if they're both flipped, right? Yeah, they're either both positive or both negative because their product is negative, but we don't know which one we have. And so if they're negative, which one would be x? X has to be the bigger of the two, right? So what would that be? Careful, -5 is smaller than -3. So x would have to be -3, and y would have to be the -5. If you want to do this out, ever, if someone's sitting there going, right? You can do this out. The way you could do it is through substitution. You could say, all right, I'm going to say, let's say I want to replace and find x. I could call y 15 over x. And now I'll plug that back into my previous equation where I see y. So I'd say x minus 15 over x equals 2. And then since I don't want x in the denominator, I could multiply the whole thing by x. X squared minus 15 equals 2x. And now if I get this into standard form, we see quadratics in where I get 0 on one side. Some people will automatically set quadratics equal to 0, and that's a mistake. We don't know that every quadratic equals 0, but we know that if it equals 0, we're able to find their values. Because to get 0, you have to have 0 basically when you're multiplying. If I multiply two things together and get 0, I know one of them is 0, and that's a special thing about having something equal to 0. So this will come up a lot when you're doing quadratics. I'm emphasizing it less today because I want to focus on the patterns where often you don't have to think so deeply about that, but it certainly is something that can happen. And so then I'd say, all right, what are two numbers? If you remember this from school or from working through books, two numbers that add to -2 and multiply to -15. I know I need 5 and 3. The -15 here tells me I need a positive and a negative. This tells me that the larger one, the more extreme value is the negative. And so I'm going to have x minus 5 times x plus 3 equals 0, which means to make 0, either x is 5 or -3. The signs flip. So I went through that fairly quickly because that's not my focus today. But recognizing that, that kind of setup and being able to do that is a very important part of understanding quadratics as well. So we'd say, hey, x is 5 or -3, and complementary y will be whatever combines within either of those equations, and it should work out both times. If I plug in x5 here, then I would need y to be 3. If I plug in x is -3 here, I would need y to be -5. Okay, so I don't know what x and y are, and I don't know their sum, although I do know the absolute value of their sum, right? I know that they're either 8 or -8. And it's interesting that that's something I knew both times, right? Look, last time I didn't know whether x was 4 or 3, and whether y was there for 3 or 4, but I did know their absolute value of their sum, right? Because if the numbers are 1 apart, then the absolute value of the difference is 1. And here the numbers are in both cases 8 apart. Sorry, we're dealing with a sum this time, sorry. So we knew the absolute value of the difference last time. Now we know the absolute value of the sum. So these combine to make 8 or -8. So the absolute value of the sum is 8. So we don't know the actual value, but we know the absolute value. So interestingly, even though these are different, we know a lot of the same stuff. In a case where they were both positive, I would actually be able to find this one too. So if my solutions were both positive, then I can know x plus y without knowing which was which, right? So so I wouldn't necessarily have to worry about that. But when there's a positive negative case, then even then I don't know whether what x plus y is. Okay, questions on that? Oh, and I had a question earlier about why we couldn't find this one. And yeah, that was an error on my part. So we were able to find this. We added it back in. We just didn't find it directly. So I skipped it for a second. I forgot we wanted to go back and find it. How do we know if there are two solutions if we use substitutions only? In general, when you see incompatible statements like this, you're going to get a quadratic. And the idea is that if I have something like x, or I'll use different variables for once. If I have something like a plus b equals 10 and a minus b equals 3, then I can stack those or substitute them. But stacking is often my favorite way to do it. I'll just add these up, the b's cancel, and I get, hey, oh wait, I think I wrote that wrong. Oh yeah, I wrote that wrong. I was gonna say that's gonna give me a weird A. I didn't want that. Let's say I have like, just do 7. So it ends up being 5 and 2. So if I stack those together, then I get, hey, 2a is 10 and a is 5. But what we should expect is if you see something like x minus y and x times y, or x plus y and x times y, I can't stack these. And when I substitute them, I'm going to end up with one of them in the denominator. And when I do that, I end up with a quadratic equation. That's not an immediate guarantee of two solutions, because if it's a perfect square, it might work out, right? If I know that it's like x minus 4 squared is 0, then x is just 4. That's that. But anything else, I'm going to have two equations. So that's how I can expect it. And the fact that these are integers doesn't actually matter. These just happen to be integers because I picked things that work out to be integers. If this doesn't say these, I never said at any point these had to be integers. It just that's what we got when we worked it out. The GMAT is generally going to give you things that work out as integers because otherwise it becomes a lot of work. For instance, some of you may have memorized the quadratic formula. You will probably never need that on the GMAT. That generally is something applicable when you're trying to find really annoying non-integer values And that's not generally what the GMAT gives you. It's not a test about kind of like hefty calculation. I also had a question about how we got 64. The idea was it's very similar to how we got 1 here. If I know my perfect square, in this case, x minus y, when you square that gets you 4. Then I know 2xy, I can know what happens when I add 2xy, right? And subtract 2xy. Now here, I was starting with it already minus 2xy. So I add 2xy, I get 34. And I add 2xy again, and I get 64. Whereas here, I got x squared plus 2xy plus y squared. So if I subtract 2xy once, I get 25. And I subtract it again, I get 1. If I had been given this, if I had been given 25, then I can add to get the big one and take away to get the little one. So in both cases, I was going from either minus 2xy to nothing to plus, or from plus 2xy to nothing to minus. That's kind of how I did it. Does that cover everybody? So let's see how this plays out on some data sufficiency questions. Okay, yeah, I'll cover the non-integer one more time. The basic idea is simply that these are the only values that work when you factor it. And so we're not just saying what are the only integer values. Nothing else will work, because what we're saying is anything bigger or smaller and it'll be different. In other words, think of 2 numbers that multiply to 15. Okay, so we said 5 and 3 work. Sure, I could have non-integers that multiply to 15, but they won't also subtract to 2. So if I had, say, 7.5 and 2, okay, the difference is 3.5. And so I'm not going to be able to have a pair of non-integers that works for both equations. Right, so 4.999 times a little more than 3 will give you 15, but when you subtract 4.999 minus a little more than 3, you will not get 2. That's the problem. You can connect this for a second. It's a little farther afield than I want to go today, but just a quick connection. You can connect it to geometry. You might know the idea that if you have a given amount of say, perimeter of fencing, the most efficient way to use it is to make a very regular shape, like a circle or a square. So let's say I have straight fencing. I'm not going to make a circle, right? And let's say I have 16 feet of fencing. Or let's say I have 24 feet of fencing. When I make the sides all 6, that's going to give me the most area I can have, because 6 times 6 is 24. Now I can have other things that add up to 24, but they're not also, did I say 6, 24? 6 times 6 is 36, losing my mind. 6 times 4 is 24, 6 times 6 is 36. So I can have other things that will add up to 24, but they won't also multiply to 36. So if I extend this a little bit, maybe I make it almost a square, but it's a little bit oblong. And so maybe now it's just 6.1 and 5.9. That will still add up to 24, but it will not multiply to 36. And before I punch this in my calculator, I can predict that it's going to be less than 36. I don't know exactly off the top of my head what 6.1 times 5.9 is, but I know it's less than 36. And when I do it, 6.1 times 5.9, I get 35.99. And so the idea is if I have 2 numbers that multiply to get a given term, and I twist them a little bit, they no longer multiply to get that 2 term. And if I find another 2 numbers that multiply to get that same term, they will no longer add or subtract to get the same term. Exactly. So when I know the sum and the product, there's only going to be one. I wouldn't say there's only 2 coordinates. Oh, yeah, there's only 2 different possibilities. Yeah, exactly. Generally speaking, unless there's some other kind of twist or unknown going on, yeah, if you have a sum and a product, there's going to be 2 possibilities. There's going to be 2 values of x with 2 corresponding values of y. That's right. Which relates back again to geometry, to your slope-intercept formula for a line, right? So yay, we're connecting geometry today. I hope that helps. But I want to try out some, just to round out our quadratic thing today, I want to try out some data sufficiency with quadratic patterns. So be careful with these. One thing you want to remember if you're still fairly new to data sufficiency is always try to say, what is it I really want to know? And how much do I really need to know to do this? Don't just hold out for the maximum that you'd like to have. What do I need to have to answer the question? I did not put up the answer choices for data sufficiency. If you need a refresher of those, I can type those up while we're working. But let me have you pull this in when you're ready. I'll give you about 2 minutes on these. So if you're watching this on the recording, I may stop people early if a lot of people are done, but I'll give you about 2 minutes to try this out and see what you get. Here we go. All right, let's see what we've got. If you haven't already got an answer, you can go ahead and pull that in. Let me know if you're at all uncomfortable with the data sufficiency part of this. I'm assuming that people have seen this to some extent, but the basic idea is we're just saying, do I want statement 1 to answer? Just statement 2, do I need to combine them? Can either one work by itself, or can I just not solve? Okay. So I'm seeing a lot of support for statement 2, for B, and you are right about that. I will spoil it. You are right about that. And the idea here is that I want to recognize my special product, right? If I want a squared minus b squared, I know that ideally what I'd like is a plus b times a minus b. And I could look at statement 1 and say, ooh, but that gives me a minus b. That's a start, but it's not enough, right? So it's a start, but it's not enough. So if I rephrase this as, hey, what's a plus b times a minus b? That's how I could start looking for this. Then I look at statement 1 and go, ooh, that's part of it. But now I'm still saying, okay, a minus b is 2, but what's a plus b times 2? I still don't know what a plus b are, what a plus b is. So if I write down my AD, BCE, which is how we generally handle the data sufficiency answers, statement 1's not sufficient. I can get rid of my top row. Now, statement 2 does not give me what I might have liked, which is a plus b. And then I'd say, ooh, it's C, put together a minus b and a plus b. It didn't give me what I expected, but a lot of you said it's sufficient. Why? Yeah, we talked about the, larger powers. We can split this one up. I can say, oh, on the left, hey, that's a difference of squares itself. I can call this a squared plus b squared times a squared minus b squared. And on the right, I can call that 8 times a squared plus b squared. And if I do that, I can see that I don't need to know all the details because some of this is just going to go away, right? I want to know a squared minus b squared. I want to know this. And right now it's got a lot of junk around it. But if I know a squared and b squared are on both sides, I can divide by that. Now, some of you might have an instinct not to divide by an unknown. And there is a caution we have to have here. So why is it okay to divide by this unknown right now? Why is that okay? Yeah, here, we're talking about, are these things integers? Are they not zero? I told you they often bring this up. They mention they're non-zero, which is important, not because I care if A itself is a zero or B itself is zero, but I care if the sum is zero, right? And if they're both squared, neither of them is gonna be negative, right? So that's not an issue. But I care if they were both zero because then the whole thing is zero, and that's another possibility I'd have to consider, and that can come up. But if I know they're not zero, then I know the sum isn't zero, and I can divide both sides by it. So now I just say, hey, a squared minus b squared is 8. That one's sufficient. Statement 2 sufficient. My answer is B. Okay. Questions on that? How are we feeling? Okay, let's try putting this together on another one. All right. Let's see. Here's something a little different. Let's see what you can make of it. Again, I'll give you about 2 minutes. All right, if you're not sure on this one, go ahead and pull in a guess. A good habit to get into. Okay. So this one has a little bit of sneakiness to it, and this is a lot harder. I'm getting a wide array of answers on this one. first off, this did not have, well, this definitely relates to quadratics. This did not have a quadratic template in it. It's not about the difference of squares or the square of a sum or the square of a difference, although it, looks a little bit like those. There's also an interesting element to this where they give us a cube term, and a cube term, cube term clearly isn't a perfect square. I can't break it up into, x squared plus this, x squared minus this. And so I can expect to have an extra solution when I have a cube term. So just like when I have a squared term, I can expect to have two answers most of the time, unless it happens to be a perfect square. And even then I'd have to know whether it's positive or negative, right? I might just have one or might have two. When I have a cube term, I can expect three solutions typically. So how would I go about working with this or factoring this? Yeah, I can move stuff over, but I need to take out an x. So I can take out an x before I move stuff over or after. It might be easier to do it first. So get everything on the same side. And again, if I can get things equal to 0, then I will. Some people would like to start with statement 2 first, and that's fine. A fun move you can do if you've never done this, if you know statement 2 is not sufficient, hey, is x 1? Well, it's not -2. You'd say, so what? Well, what can you get rid of? B and D automatically. If I know the statement's not sufficient, then I can get rid of the one that corresponds to just that statement, and I can get rid of D. And so that could be a quick way to get it down if I were in a hurry, if I weren't sure, I could at least know that much. For statement 1, I can get things on the same side, and then I can pull out an x. So that would look like this, and then I'd pull out an x. Now, at this point, I could, for instance, try dividing both sides by x, but I might get myself in a little bit of trouble with that. Some of you who missed this one might have gotten in trouble at this point. Why don't I want to divide both sides by x at this point? It's always like, hey, was there a money back guarantee or not, right? So this time it didn't tell me whether x was 0, and so I can't divide by it. I have to recognize that that's one of the possibilities. One possibility is that x is 0. And that'll actually play out if I factor this. If I pull an x out, I'll have this. And then I can say, here I have to use my quadratic skills and say, all right, what adds to +1, my coefficient here, and multiplies to -2? And I'll have this, x plus 2, x minus 1. If you FOIL this out, you can check it. X squared minus x plus 2x minus 2 gives me this. Notice I then have 3 roots, 3 zeros. X could be 1, x could be -2, or x could be 0. So if you got C on this, you might have overlooked the 0 possibility, right? One way to think about this is, hey, if I factor x out, then I just get -2 and 1, but that's assuming x isn't 0, so I got to think about that possibility. Another way is to simply leave x in and say, all right, there's 3 different things that can make my 0 here. If this product equals 0, either this is 0 and x is 1, or this is 0 and x is -2, or x itself is 0. So this is the least satisfying kind of data sufficiency, where nothing at all is sufficient. It's got to be E, right? Statement 1 didn't work. If I put them together, that gets rid of -2, but I still had 2 other solutions. My answer has to be E. Okay, thoughts on that? All right. If you have places to go, feel free to head on your way, because I know we're at the hour. But if you would like to stick around for a bonus question, I want to toss you a bonus question. In case you do have to go, definitely hope I see you around for one of our classes. Any questions you have, feel free to chat them in. Other than that, I'm going to toss you your bonus question, and we'll clear out after that. So here we go. Okay, let's get in those answers. See what we can do. So this is a little odd. It's got roots in it. We haven't talked about roots, right? We've been talking all about putting together quadratics. So what do roots have to do with quadratics here? How are these connected? I'm seeing x and x plus y and x times y. We've dealt with a lot of that today. So what's the connection? What can I do? Yeah, I can find if I think about the square of a sum, I can get from the square of root x plus root y to something else, right? Now notice that I can't just square directly. In other words, I can't say, oh, if I square this, I get x plus y, and I square this, I get 25. If so, then x plus y would be 25. X plus y is only 15. Similarly, if I'm certainly allowed to take the square root of both sides. I can do this, right? And that, it just isn't the same thing. Square root of x plus y is not the same thing as a square root of x plus a square root of y. Root 15 is just under 4. Root x plus root y is 5. It's not the same thing, so we got to watch that. However, if I square this expression, then I'm going to get, hey, I'm going to get the square of this and the square of that and 2 times the middle. So just like I know that a plus b, whoops, a plus b squared is a squared plus 2ab plus b squared. I know that this root x plus root y squared is going to be x plus 2 root xy plus y. So I can know that. All right, so if that's bugging you, let me know. But then I can use that to solve pretty readily, because I can just say, all right, well, if that's true, then I know I have x plus 2 root xy plus y is 25, and I know what x plus y is. This is something you'll often see on a data sufficiency form where you go, ooh, one of them gives me x plus y, and that gives me, oh, I got that. And they can do every variation on it. One of the statements could give you this first part, and another statement could give you that, and it's C. Or maybe the question stem gives you one part, and one of the statements gives you this part, and then it's just say A or just B, right? So there's variations they can play with that. And so then when I run with that, I subtract and find the difference. 2 times the square root of xy is 10. Root of xy is 5. So xy is 25. All right, so congrats to those of you who got that. Good work. But that's our bonus for today. Any questions on that one? All right, folks. Well, the classic combination of Chinese food and tacos is calling my name. So but I will take questions before I deal with any of that. So if you want to check out any of our classes, here's a link to do that. We have courses, we have tutoring, and we have lots of these workshops available for free on YouTube. So feel free to check them out if you're not already doing that right now. Thanks, everybody. Yeah, if you have a question on that last problem, let me know. All right. I'll stop the recording, but I'll take extra questions if you have. All right. Thanks, everybody.